see it, but I just want to highlight there is this aspect ratio, A, B, where we have the aspect ratio taking B divided by A in the following table over here. All right. So in cases when it's non-circular cross-section, so again, this is another consideration. We have been talking about circular cross-section, so now another configuration, non-circular configuration, of which now we need to find out our diameter. So this equation over here, dH is what we call the hydraulic diameter. So we can think of hydraulic diameter as the kind of like average diameter for a non-circular shape. Say, for example, a square cross-section. What is that so-called diameter? There's no diameter in the square. There's length and breadth, but there's no diameter. And then we need some sort of diameter to put into our Reynolds number, because our Reynolds number would have the need of having a diameter. So we kind of like say that, okay, let's arrange it such that we call hydraulic diameter. And the hydraulic diameter is given by 4 multiplied by the cross-sectional area of that square shape, cross-sectional area, divided by the perimeter of that section. So this one here refers to your cross-section of your non-circular pipe. And this T over here refers to your perimeter. Again, of the non-circular pipe. So it's only with that we could find out what is the diameter that we can use later on for looking for things like your Reynolds number. This has a spelling error, this previous. So it's important to note that if your question is about a non-circular duct, please calculate your hydraulic diameters instead of using one of your value like the length or the breadth. So use your hydraulic diameter. The dimensions A and B normally will be given. Now there are 3 things that we can do to enhance the heat transfer. So just now we were talking about your heat transfer using the Newton's cooling law, that is Qs equal to H multiplied by the surface area when heat is transferring out perpendicularly, radially, and multiplied by the temperature difference. So that heat can transfer out, there must be a temperature difference. So in order to increase this Qs value over here, if we want to increase Qs value over here, you could see that in this equation, there are a few things that you could increase. Either you increase H, increase As, or increase delta T. Delta T will be the temperature of where the flow is in the pipe compared to what is in the ambient. This is your delta T. If there's a temperature difference, then heat can transfer out. Normally, your flow would have the heat that you want to remove, get transferred out, and the ambient temperature is fixed. So delta T tends to be a fixed value that you can't change much because the ambient condition is fixed. So what we can do is to look at how can we change H and how can we change AS. AS is the surface temperature, surface area. Surface area of the pipe where heat is transferring either in or out, depending on which side is hotter and colder. Right. Note, AS is not AC. AC is a cross-section of the pipe. So if you have a pipe, cut it, look at the cross-section, that is your cross-sectional area. AS is that if you have a pipe, and that's internal surface area of the pipe, that is AS. So these two refers to the different areas. And so a lot of students make this mistake. You have to understand where is heat that's transferring out perpendicularly. So in the case of a pipe, it's radially, but generally you could say where heat is transferring out perpendicularly. So let's look at what are the strategies that we can use in order to improve QS. So the first method is this one. What we're going to do is that in the pipe, this is the pipe, what we're going to do is to insert a spring going inside. So the spring is kind of like zigzag, but if you imagine the spring goes that way, right? It goes wind up in that way. Now, why do we have string going inside of a pipe in that way? That's because you can see that as fluid were to flow inside the pipe now, it will flow through a very rough surface because now it's lined up with that spring. So as a liquid or as the fluid flows in there, there are a lot of bumps around the surface of the internal side of the pipe. And this bumps is good because the bumps will introduce more turbulence, more mixing, and if it's turbulent, your H value will increase because your H value depends on the surface roughness of the pipe. The larger surface roughness it has, the larger H value you will get. And if the larger H value that I get, my heat transfer rate will increase. That is desirable. These are the strategies that we can use to improve the heat transfer. Some students may ask, wow, it sounds like inside is kind of very rough for the fluid. Yeah? Doesn't it mean that it's harder to pump? Yes, that's a very good observation. If it's so rough in the inside of the pipe, you actually require a larger pumping force to pump the fluid through it because now it's rougher inside. So there's this give and take thing. You wouldn't want to increase the surface roughness to the extent that it's so rough inside that you require a lot more pumping force from your liquid, from your fluid pump, from your centrifugal pump, for example. If more pumping force or pumping work is needed, more energy will be needed. So you'll be asking yourself, am I really having more heat that's transferred at the expense of using more energy? So because more energy will be used to pump. So that's one thing. Next thing is that if you look at the set of equation, there's this part that's surface area. Now this surface area refers to the internal surface area of the pipe, internal surface area. That internal surface area, if I have a lot of that surface area, I'll get more heat transferred. Why? Because from this equation here, it says that if I have AS here increase, my QS will increase. In order for us to increase that surface area, what we can do is to have that surface area. Where is it? I think I deleted it. Come back. Okay. So what we can do is to increase this surface area. So you could see that there are some things that's lined inside this tube. So if I have that surface area increased, then more heat will get transferred. Might be in or out, depending on which side is hotter and which side is colder. But the idea is to increase that surface area. This is your second strategy in order to increase heat transfer. The third strategy is to introduce swirl by inserting twisted tape. So I hope you can visualize. What I have is a tape over here. So this tape, kind of like as it move along the pipe, it twists. So it twists in this kind of shape. It twists around. Why would I need a pipe with a twisted tape inside? That's because that fluid flow would now be kind of like spiraling along the pipe. Why would spiraling be desirable? Compared to if you put a spring in there to increase the surface roughness, this swirling, in a way, also generates that turbulence. And if you have fluid that's flowing instead of along the pipe, if you have fluid that's flowing kind of like cutting the surface of the pipe, fluid that's flowing in that way, that actually increases your heat transfer coefficient H. So this is also another strategy to increase your heat transfer. So please take note, there are these three ways of increasing the amount of heat transfer. Not sure what this camera is. Not sure if I haven't seen it, but it looks like a good question. So let's dive into the next section, which is talking about natural convection. So for the natural convection, there are two figures over here. This figure at the top here is for forced convection. And in this figure over here is showing where you have natural convection. Actually, that's a good figure over here. If you go to OIP, your Overseas Immersion Program, in Scotland, you get to see these kind of devices. Please take a picture, and maybe if you could send it to me so I can show it to your juniors next time. You'll be going, I'm not going. Oh. I'll try to do something next year. So take this picture, and what this is actually residing in all your hostel rooms. It's for heating. Right? During summertime, sometimes they off it, but maybe for Singapore students, a little bit like like 10 degrees is quite cold. 10 degrees is actually not cold. So you will have this heater that's turned on. What happens is that inside the heater there will be hot fluid that's flowing through this kind of network. It will go through there and then it will come out there. So the idea is that the hot fluid here will create that convection, heated air, and then the heated air will heat up the room in that way. So this is called a house heater. So obviously supplied by a pump system and a heating system, and then you will supply the entire building with this sort of thing. So you could have this kind of a heater naturally convected. That means you just leave it there because the air that's around this heater will get heated up and then it's become buoyant and then your hot air will rise. And this hot air that's rising, it will go on to heat up your entire room. So it's different from our air conditioner. Our air conditioner, you can see, is always located at the top of the building. It's never at the bottom of the building because cold air would sink. This heater in Scotland is all placed at the bottom part of the building. Particularly, they will be placed near the windows. That's because that's where cold air or the coldness from the outside is going to get. You're going to get it from there. There's not much thermal insulation around the windows, so they put it below the windows. Hot air would rise, and then so that you will keep the rest of your room insulated from the cold. So that's what it is. You have it placed near the door. Actually, the right location will be under the windows. So we have that circulation that's going around the room, hence insulating the room from losing heat outward. So some of the examples where natural convection can be found will be things like, for example, if you have your audio equipment, audio amplifier especially, because audio amplifier will use more electrical energy in order to amplify sound. So if you look at your audio amplifier, look at the back part of it, you have a lot of cooling fins in there. This cooling fins job is to cool down the electronic items in there. So what happens is that you can see again, just like your fin tube, where you saw just now, there are a lot of fins going on in the tube. This audio equipment will have the cooling fins to increase the surface area where heat is transferred outward. Because your electronic items will be hotter, your ambient relatively will be cooler, so heat can get transferred out. So these are some of the examples that you can find for natural convection. This one over here is forced convection, where you have flow flowing across, forced across these heated tubes. So there are a series of tubes over here, the arrows indicating where the flow is. So these arrows indicating where the flows are going. And normally this is a network of hot fluid that's going through these small little tubes. And you have a cross flow, a flow that's flowing across, that's forced across it, so as to remove heat from the hot tubes that's going through it. So this kind of thing is what we have seen already, forced convection. Now we're going to focus a little bit more about the natural convection. I think this next slide is also talking about external forced convection. So just now for a pipe system, that's internal configuration. So let's have a look at external configuration. So external configuration could be a convection that's going across the flat plate. So we have seen this before. For a flat plate, you have ambient flow that's forced convect over it. So in the case of this kind of setup, this should be a small letter U. Small letter U. Small letter U. For this kind of setup, when we start to look at the what we call the thermal physical properties, and thermal physical properties could be things like, again, like density, specificity, capacity, your thermal conductivity, your dynamic viscosity, etc. All these thermal physical properties, for this kind of setup, usually we want to find out what is the properties at what we call the film temperature. The film temperature. So note, just now it was a average temperature, average mean temperature, where we had internal flow. Right? It was an internal flow just now, where we have this part here, this temperature here as my Tmi, and that part here as my Tm naught. That was flow that's going inside the pipe. But in this slide over here, we are not talking about that anymore. We're talking about external flow. And external flow means that there's going to be a boundary layer, there's going to be a surface temperature, Ts, and there's going to be that ambient temperature, T infinity. If we need to find out all these thermal-physical properties, what we need to do is to look up the table again, and then find out what is that temperature that we are after, to find out the corresponding physical property. And that temperature will be the film temperature. So the film temperature, Tf, is equal to Ts plus T infinity divided by 2. Very similar to this, but different set of configurations. This one is Tmi plus Tmo divided by 2. So it's the average as well. But please note there are different setups, different configurations. The important part of this Tf over here, which is a film temperature, you could be given this as your surface and ambient temperature in degrees Celsius. So you calculate it out and then you'll be in degrees Celsius. But I want you to express TF in Kelvin, particularly in Kelvin, because later on we'll be making use of that. So please express your TF in Kelvin. So later on we'll make use of that. Now the next slide is sort of like a recap of what we have seen before. In fact, I was comparing it word by word. This part here, they are all very similar to the slide that we've seen before. For Reynolds number across the plate, that will be this, what we call the critical Reynolds number. And that critical point is when it's at 5 times 10 to the power 5. So the note says it's 5 times 10 to the power 5. And anywhere here, all right, that's when you have your, well, actually at this point over here. At this point over here, that is when you have your critical Reynolds number. And the length from the leading edge, this edge here, is what we call the leading edge. From the leading edge to where the critical Reynolds number is, how do I know it is critical? I know it is critical if it's equal to 5 times 10 to the power 5. And for Reynolds number, this should be REC. For Reynolds number, you would need that distance, XC. XC is from that leading edge all the way to where your Reynolds number is 5 times 10 to the power 5. That is your critical length. So XC here is known as your critical length. And the corresponding Nusselt number is given by this expression over here, where this one here is for the laminar region. So if you have a laminar region within your critical length, you'll be looking at your Reynolds number given by this expression over here. If you look at your turbulent region, that is from here, greater than 5 times 10 to the power 5, or the Reynolds number, that's your turbulent region, you'll be looking at this set of Nusselt number equation. So if you compare this against what we have in your exam data booklet, you see a little bit different. Right? This one refers to a plate, so please refer to the right equation in your exam data booklet. A lot of students read the wrong set of equations. So you gotta know the configuration that's given to you. So in this case, for a plate system, it says over here, it's given by this number. And then you compare that. This is for when it's at less than 4 times 10 to the power 5, that means laminar flow region. And then you look at this, it's 0.332 is 0.664. Kind of like quite a big difference. But actually this difference comes about because this set of equation here is for average Nusselt number, whereas this one is not average but local Nusselt number. How do I know that? That's because for the H value over here, Hx, that refers to the local heat transfer coefficient, the local one, that point. If you want to consider the Nusselt number across a certain length, say for example from where x is equal to 0 to where x is equal to xc, xc refers to the critical length. If you want this entire region over here, the Nusselt number for that entire region, that's when you have that average Nusselt number over there, and it's given by this expression over here. Okay, so that's the difference between these two sets of equations. The same goes for your turbulent flow. That's when you get to see more greater disparity. For your turbulent flow, it's given by this expression, but over here in your lecture notes, it's given as this. So again, this is a part that I was saying, Glasgow need to put your act together, which one they want. Okay? So For now, because it's not exam yet, for now, we refer to the lecture materials. So I just need to make sure that you guys are taken care of when it comes to the exam. What is a set of equations that we are using? Okay? So that will be made known to you before your exam. Now there's also external flow over a single tube. And this part here is interesting in the sense that there's one point, if you have a tube over here, and this is what we call cross flow. For a cross flow, I think there's a class. Okay. No problem. So for a cross flow, this point here is what we will experience a stagnant, forward stagnant point. That means at that point, the velocity is actually equal to zero. Nothing moves over there at that point when flow is going across, cross-flowing across that pipe. So this is a cross-section of the pipe. As the flow goes along this curved surface of the pipe, it's going to flow laminarly along that pipe until a point when it starts to have what we call the separation point. The separation point is a point just like in your plate system, you have laminar flow transiting into turbulent flow. So the saturation point is also the point where it transits from laminar flow to turbulent flow. So after the saturation point, you will see everything over here is turbulent. And we call that turbulent region as the wake of that cross flow. So the wake will just continue on in that way, and sometimes further down, the whole flow will get streamlined back again. So if you have that kind of cross flow, again, the different set of Nusselt number will be used. And I want to draw your attention to, this is actually also provided for a cylindrical cross flow. It's given by this set of Nusselt number, where you have C, N as unknown here, depending on what is your Reynolds number. So depending on what's your Reynolds number, if it lies in this different range, then your C and respective N values will be these numbers. So you'll be using, for example, if your Reynolds number is 0. If your Reynolds number is equal to 1, that lies in between here. So you'll be using a Nusselt number that is 0.989, Reynolds number to the power of 0.32, times Prandtl number to the power of 1/3. So you'll be using that set of equation. So that set of tables is already provided in your exam data booklet. And that is for the case of a cylindrical cross flow. There's also external flows over banks, and again, for that, the Reynolds, the Nusselt number is given to you in the following conditions. Now, these ones, they are not given in your exam data booklet, so I'll try to make sure that they are provided to you. Particularly, you have that banks of tubes. They are arranged in a lined manner, just like this, or staggered manner, just like this. So in each of these cases, what we need to figure out is that what is that configuration that's given to us, so that respectively we can use the right set of Nusselt number. So this one would be cross flow, again cross flow over the cylinder or banks of cylinders or tubes. So you would see that there's this NL over here, where if you want to use this Nusselt number expression, your NL must be greater than 20. That means 20 tubes over there. And we'll be expressing everything as inlet, the inlet and outlet fluid temperatures. That means whatever inlet temperature over here, Tm5, and exiting at Tmo. So we're looking at that one. Okay, we'll continue from here next week.